Hi, this is Dr. Goldstein, and today I'm going to be talking about polynomial division. So before we get to polynomials, let's just start with regular old division. So let's say that we want to take 158 and divide it by 4. So what we usually do here is we look at either the first or the first two or the first three or however many digits we need. We look at the first few digits and we ask how many times does 4 go into that. So 4 goes into 15 3 times, and then I multiply 3 times 4 and I have 12. I subtract that off and I get 3. Now 4 doesn't go into 3, so I bring that 8 down and I say, okay, how many times does 4 go into 38? And 4 goes into 38 9 times. And 4 times 9 is 36, and so I subtract that off, and I get 2. And now 2 is smaller than 4. 4 doesn't go into 2 any more times, and so this is my remainder. And what I have just discovered is that if I take 158 and I divide it by 4, I get 39 and 2/4. So when we divide, our remainder ends up still being divided by the thing that we're dividing by. So again, this is polynomial division, and this is regular long division, and polynomial division is very much based off of regular old long division. So I will show you that. Let's say that we want to take 4x squared plus 2x plus 3, and we want to divide that by x minus 2. So in other words, we are taking 4x squared plus 2x plus 3, and we are dividing by x minus 2. Now, it sounds the same when I say it like that, but remember, division is the same as having a fraction. Okay, so if I want to do this using long division, I take x minus 2, and I'm dividing that into 4x squared plus 2x plus 3. So we start here a little bit differently than we do with regular long division. I'm just going to look at the leading terms of both of these expressions, and I'm going to ask myself, what do I have to multiply by to get that? So I take x, and I say, what do I have to multiply x by to get 4x squared? Well, I have to multiply by 4x. And now I take that and I multiply by the entire divisor, the entire expression that I'm dividing by, and I end up with 4x squared minus 8x. So again, I'm taking 4x and I'm multiplying it by the entirety of x minus 2. Now, just like regular long division, I subtract that off, and I actually like to subtract from the entire polynomial that I started with. So the 4x squareds are going to cancel. I get 0 from that. I have 2x minus a negative 8x, so do not forget to distribute this negative sign. So 2x plus 8x is 10x, and then I have this plus 3 that just kind of comes along with that. I'm not subtracting any constant terms. So now again, I'm just going to look at my leading terms. I look at my x, and I look at this 10x, and I ask myself, what do I have to multiply by to get 10x? I ignore everything else. Well, I have to multiply by 10, so I put that up there, and again, I multiply that 10 by the entire expression x minus 2. So I have 10x minus 20. I subtract that off, and so my 10x's cancel. And again, do not forget to distribute that. So I have 3 plus 20. I have 23. And now again, I look at this x, and I look at this 23, and x doesn't go into 23. There's no whole number, a whole power of x that I can multiply by. In a sense, 23 is smaller than x. It has a lower degree. So this now down here, this is my remainder. And what I have found, similar to just regular integer long division, is that when I take 4x squared plus 2x plus 3 and I divide by x minus 2, I end up with this expression up here. My quotient is 4x plus 10 plus my remainder, 23, divided by the original expression that I was dividing by. So again, my remainder, this comes from the remainder, and then this comes from what's called the quotient. All right, that is polynomial long division. There is a shortcut, which is called synthetic division. So we have long division. This is a long way out of doing this. And then we have synthetic division. And I'm going to show you this quickly, and then I have a couple more examples to show you this as well. So whenever I have a linear expression, so x minus 2 is linear with leading coefficient 1. So that's what I need in order to use synthetic division. So anytime I have something, if it's like that, it's going to be of the form x minus c. Anytime I have that, I can take that value of c, so in this case it's 2, and then I make this array using the coefficients of my original polynomial. So my original polynomial was 4x squared plus 2x plus 3. So the coefficients were 4, 2, and 3. And I'm going to make this shape, and you'll see why it looks like this later. So this is synthetic division. I start by bringing the 4 down, and then I multiply 2 times 4. And I put it up here. So 2 times 4 is 8. And then I add vertically. We add. So I get 10. And then again, I multiply. I multiply 2 times 10, and I put it up here. So 2 times 10 is 20. And then I add vertically. So I get 23. Now, let's compare this to the long division. And there's kind of a lot of marks going on here, so I'm going to erase some of them. Let's get rid of these. If we look at these expressions, I have a 4 here, and that is the same as the 4 that's right here. And then I have a 10 right here, and that is the same as the 10 that's right here. Also, the 4 is up here. Get rid of this. 4 is up here, and the 10 is up here as well. So the same numbers. And then lastly, we have this 23, and there's our 23. So the numbers in synthetic division are the numbers that we care about in the long division. So again, this 23 is our remainder. Get rid of these extra markings again. So this 23, the thing that goes in the box here, this is our remainder. And then if I look at how I set up this grid, this 10 here, this is our constant term. So I multiply that by 1. This term here is going to be our linear term. I multiply that by x. If I had another term, I'd multiply it by x squared. So when I read off my final quotient from this, my quotient is equal to 4 times x plus 10 times 1, and I have a remainder of 23. And so I get the same answer. It is 4x plus 10 plus my remainder, 23, divided by x minus 2. That's synthetic division. And again, I'll show you another example where I'll use it. It's actually much, much easier and much quicker, but it's a little mysterious. It's a little bit like, wait, what? How? What are you doing? Why do I follow that? It's just a process. Okay. So let's look at another example. We want to factor f of x equals x cubed minus 5x squared plus 3x plus 9. So we'll get to the long division eventually, but first, this is a cubic, so I want to try something easier if I can. So I could say, okay, could I factor this by grouping? That would certainly be easier than what we were just doing. So if I take an x squared out of the first two terms, I'm left with x minus 5. And I could take a 3 out of the third and the fourth term, so that just leaves me with x plus 3. There's no common factor. So grouping's not going to work. Another method that my last video was about is the integer root theorem. So the possible integer roots are going to be the divisors of 9. The positive and negative divisors of 9. And so that could be plus or minus 1, plus or minus 3, or plus or minus 9. Now I don't know if these are actually roots, so I'm just going to plug them in and check. So are they roots? If I plug in 1 to f, I end up getting 8, so that's no. If I plug in minus 1, I get 0, so yep, x equals minus 1 is a root. If I plug in 3, I get 0, so there's a second root. So far, so good. If I plug in minus 3, I end up getting negative 72. If I plug in 9, I get 360. And if I plug in minus 9, I get negative 1,152. So this makes me a little bit sad, because if I really want to factor this all the way just using the integer root theorem, I need 3 roots. Not just 2. To factor completely. So what I need to think about now is, if x equals c is a root, then x minus c is a factor. So meaning that f of x is equal to x minus c times something, i.e., if I take f of x and I divide it by x minus c, I'm just going to get a polynomial. So meaning the division is nice, and if I want to know, well, what's the rest of this polynomial that's not just this x minus c, I can divide. So we divide by x minus c, where x equals c is a root. Now I have 2 roots here. I have x equals minus 1, and I have x equals 3, and I could do either of them. I just have to pick one. So I'm going to do x equals minus 1. So I'm going to divide through by x plus 1, just because it was first, so why not? So I have x cubed minus 5x squared plus 3x plus 9. Again, you could do x minus 3. That would be fine too. So if I look at the leading terms, x and x cubed, I have to multiply by x squared. And so then when I multiply x plus 1 by x squared, I end up getting x cubed plus x squared. And I subtract that whole thing off, and I end up getting, so remember, distribute, I end up getting minus 6x squared, and then plus 3x plus 9. Those just come down. If I look at my leading terms, the x and the minus 6x squared, so I have minus 6x. I multiply by that, and so I have minus 6x squared, and then multiplying by that 1, I have minus 6x, and I subtract that whole thing off. So I have a 0 and then plus 9x, and then I have that plus 9 from before. And then again, just looking at this x and looking at that 9x, I have to multiply by 9. And so when I multiply, I have 9x plus 9. And hey, look, when I divide, when I subtract that off, I get a remainder of 0. And remember, this is what we wanted because we're dividing by a linear factor that we got from a root. So we have to have that. We have to have a remainder of 0 because this one is supposed to divide nicely. So what I get is that f of x is x plus 1 times this quotient up here, x squared minus 6x plus 9. Now, I could divide by x minus 3, but at this point, I just have a quadratic polynomial, and it's so much easier to just factor it. So I have this x plus 1, and then if I want to factor x squared minus 6x plus 9, that's just x minus 3 times x minus 3. And there's my other root. My other root was x equals 3, and it just so happens that that one occurs twice. So that's my answer. That is my fully factored polynomial. So let's look at this process again using synthetic division. So if we want to look at this using synthetic division, my x minus c over here, this is x plus 1, which is x minus negative 1. So c is equal to negative 1. So I have this minus 1 that I'm dividing, and then the coefficients of my polynomial are 1, minus 5, 3, and 9. So again, this is the coefficient of x cubed. This is the coefficient of x squared, of x, and that's my constant term. Okay, I have my remainder box down here, and I begin this whole process just by bringing the 1 down. I multiply by minus 1, and I bring it up here. And then I add vertically, and I end up with minus 6. And I multiply by the minus 1, so I get 6. I add vertically, and I get 9. I multiply by minus 1, I get minus 9. I add vertically, and I get 0, which is exactly what we expected. We have a remainder of 0. Now, when I turn this back into my answer, this is my constant term. This is linear, and this is going to be x squared. So what we have is that x cubed minus 5x squared plus 3x plus 9, when I divide that by x plus 1, I end up getting x squared minus 6x plus 9, meaning that our polynomial that we started with, f of x equals x cubed minus 5x squared plus 3x plus 9, is equal to x plus 1 times x squared minus 6x plus 9, which is exactly what we got before. And again, you can take that x squared minus 6x plus 9 and factor it as x minus 3 times x minus 3. And so all in all, our fully factored form is x plus 1 times x minus 3 squared. So polynomial long division and synthetic division can be kind of complicated to get the hang of, so I recommend that you go, Khan Academy has some great videos of especially synthetic division if you just look it up. So I definitely recommend finding more videos on this topic because it can be confusing, but hopefully this was still helpful.